Okay, so we are going to pick up where we left off with combinations. So let's just do a quick review of permutations, just because combinations and permutations are so closely related. So permutations, if you remember, is an arrangement in which order matters. And we came up with this really nice formula for it. We said NPR is n factorial over n minus r factorial. Okay, but so for example, 10 p6 is 10 factorial over 4 factorial because 10 minus 6 is 4. 15 p3 would be 15 factorial over 12 factorial because 15 minus 3 is 12. Okay, this is essentially saying do 10 factorial but stop after 4 numbers. Stop after 6 numbers. So for example, 10p6 would be, okay, start at 10, go 9, 8, 7, 6, 5. Stop there. There are 6 numbers. This division by 4 factorial is what gets rid of the 4 times 3 times 2 times 1. Okay? 15p3 is 15 times 14 times 13. So we're saying do 15 numbers, stop after 3 of those numbers, and the 12 factorial is what cancels out everything that would come after this. The 12 times 11 times 10 and so forth to the times 1. Okay, so this would be the number of permutations. Reason for this is every spot represents an event. The event is always the same here, so it might be picking people, it might be picking objects, it might be building a Lego tower. And we're starting off with the number of things that we have. So we have 10 things to choose from, and we're going to choose 6 of them. So there are 10 possibilities for the first open spot, then 9, then 8, then 7, then 6, and then 5. Okay, so the N is the number of things we have. Again, things is very broad here. And R is the number of things we're choosing. And we're saying N always has to be greater than or equal to R. Because we must have more than what we're choosing. We also said NP0, okay, if we're not choosing anything, we're saying that there's only one way to do that, one arrangement in which we choose 0 things, okay? So during the last video, we ended on a definition of combinations. So we said combinations is an arrangement in which order doesn't matter. So there are very similar ideas. We have the same concept here. We have NCR, where N is the number of things we have, and I'm sorry, we didn't use R, we actually used X. I'm accustomed to using R. I'm gonna change these to X though, because that's what I had it before. I'm just changing all these to X's. some textbooks use R, it doesn't really make a difference. It means the same idea. It means the same thing. It's just the number of things that we're choosing. So again, the N here is just the number of things that we have. And the X is the number of things that we're choosing. We'll say N C X, but a lot of times you'll hear it pronounced as N choose X. We're choosing X things. Okay, so if you see this is just NPX, we typically wouldn't say N permutation X. Same way we typically would not say N combination X. But when you see this, a lot of times you will hear people saying N choose X. We do have a way of saying it, okay? The difference here is that what we're saying is if we have A, B, C, D, just take the letters. Okay. I'm going to include E. So we have 5 letters. This is saying is that there are 5 factorial permutations. Okay, so we would have 5 possibilities for the first letter, 4 for the second, 3 for the third, and then times 2, sorry, I ran out of space here, times 1, okay? There is only one combination. So A, B, C, D, E is the same thing as E, A, C, B, D, which is the same thing as D, A, C, B, E, which is the same thing as A, C, E, B, D, and so forth. All 5 factorial combinations, permutations, is the same combination. There is no difference. So at the beginning of the last lecture, I talked about how a combination lock is really a permutation lock. Well, now you see why a combination lock is such a wrong term to use for it, because the order does matter. And if you have 4 digits in your combination lock, there are 10,000 possibilities. But if we're saying that order doesn't matter, then we're saying that there's only one combination or only one possibility. So it does make a very big difference. Okay, so let's say that instead we're not choosing every letter. So we know if we're choosing every letter, okay, if it's 5C5, for example, 5C5 is equal to 1. That's what this is telling us. If we have 5 things, in this case letters, and we're choosing all 5 of them, there's only one combination. That's what this is telling us right here. But let's say instead that we're only choosing 3 of these letters, okay? So if we're only choosing 3 letters, then this changes things. So one possible combination is ABC. Now this is different from ACD. These are different. It's not the same. They involve different letters. They involve the same letters, they're the same combination. But these involve different letters, so they're different combinations. So if we're only choosing 3 out of the 5, then all of a sudden it's not 1 anymore. Let's keep going. ACD is different from BCD. And BCD is different from EAD, and so forth. So let's think about what's going on here, okay? If we were talking about permutations, so for the number of permutations, we have 5 things. We're choosing 3 of them. So that tells us that we have 5 times 4 times 3, or 60 permutations, okay? Notice we didn't write out all 60. We just wrote out 4 of them. But this is less, because this is saying ABC is different from ACD, but it's the same as BAC. And that's the same as ACB. And that's the same as BCA. It's the same as CAB. And it's the same as CBA. All of these are the same. So we have different combinations, but we also have a lot of repeats here. For this one, there are 3 times 2 times 1 repeats. That's because we can either have A, B, or C, right? For here, we can say that we can have A, B, or C as the first letter, which means that we have whatever we didn't use as the second possible letter in these repeats. And we could have what's left over as the third possible letter. So for each one of these, there are 6 repeats. Now the same is true for all of these. So for the EAD, there are 6 repeats here as well, because either E is first, in which case we have EAD or EDA, or A is first, in which case we have AED or ADE, or D is first, in which case we have DEA or DAE. So for every permutation, there are 6 repeats. And we have to get rid of these. And the way that we get rid of repetition, just like over here, the way that we get rid of repetition is to divide. So the number of combinations would be saying, okay, take the number of permutations and divide by the number of repeats of each individual permutation. How many repeats are? Well, the number, the number of repeats is equal to the number of different ways that we could arrange each permutation, which is 3 factorial. If we have 5p3, well, 5p3 is telling us that we're choosing 3 things. And if we're choosing 3 things, there are 3 factorial ways of arranging those 3 things, because there are 3 possibilities for the first, 2 possibilities for the second, and 1 possibility for the third, or 3 factorial ways to arrange each permutation. That's true here, that's true here, that's true here, and because it's true for all of them, we use division. So this is 5 times 4 times 3 over 3 times 2 times 1. So this is, now there are 6 different permutations. I'm sorry, not 6, 10. 10 different permutations. Let's look at it differently. So suppose now we have the letters. We're just going to choose some at random. B, T, Q, U, R, and S. Okay. So we're going to choose 4. And we want to know how many combinations. Well, let's show some of the permutations. Okay. So we have B, T, Q, U. That's one example. We have R, S, T, U. That's another one. Let's say that we have T, R, S, Q, and so forth, right? So we have a whole bunch of these. And if we want to know the number of permutations, it would be 6 times 5 times 4 times 3. So let's just write that down. We'll do it up here. Number of permutations is 6p4, or 6 times 5 times 4 times 3. And there's a lot of these. 6 times 5 is 30. 30 times 4 is 120. Times 3 is 360 different permutations. Well, let's see how many different combinations. So these we know are different combinations because they involve different letters. So BTQU is different combinations from RSTU. In order to be a different combination, they have to have different letters, okay? I'll put that down here. They have to have at least one different letter. So that's true in each of these cases. BTQU has different letters than RSTU, and RSTU is different from TRSQ. Here, all of the letters are the same except for the Q and the U, so they only have to vary by one letter, okay? And there are different combinations. So all of these are different. So let's just make sure that we put that in. These are different combinations. They have at least one letter that's different. Okay, and there are a bunch of them. But now under here, let's list, I'll do it in blue, okay? Let's list some permutations that are identical. So for example, B, T, U, Q, this is the same, okay? It's a different permutation, but it's the same combination. The same thing is true with this one. It's a different permutation, but it's the same combination because all the letters are the same. Here's another one. Here's another one. Okay. These are all of the different permutations that have a B as the first letter. But we could have a permutation that has a T as the first letter. Okay, and these keep going. So these are the same combination, but different permutations. So if we want to calculate the number of combinations, what we need to do is we need to get rid of these repetitions. Okay? So how many repetitions are there for each one of these? We're saying the number of repetitive combinations for each permutation. In other words, this is the number of permutations that have the same letters. Well, each permutation has 4 letters. If we take this one, for example, there are 4 possibilities for the first letter, B, T, Q, or U. Now we've used one of those, so now there are only 3 for the second letter, 2 for the third, and 1 for the last. So for each of these, there are 24 permutations that are the same combination, okay? So here, the same thing is true. There are 24 repetitions here, 24 repetitions here. So how do we deal with that? We're going to take the 6p4 and we're going to divide by 24. So the number of combinations is 6p4 divided by 4 factorial, or 360 divided by 24. So if we open up our calculator and we compute this, 360 divided by 24 is there are only 15 combinations. So you could see how much fewer there are. How many fewer? There are 360 permutations, but only 15 combinations. Think about how many repetitions that means that we have, okay? So let's generalize this and come up with a general formula for the number of combinations. So the number of combinations, what we're saying is it's the number of permutations divided by the number of times each permutation repeats. So NCR is NPR. I'm sorry, I used R again. When I've taught this previously, I always used R, that's why. But the textbook that I'm looking at uses X, so I'm going to use X. So it's NPX over X factorial. Okay, because that's the number of times that each permutation is going to repeat, right? We're using all of the letters in the permutation, which is why we have X factorial and not something like XP something, okay? It's X factorial because we're using all of the letters that are here, and this is telling us how many letters are in the permutation, right? At 6P4 tells us, okay, we've chosen 4 things, so there are 4 letters in the permutation. And we're looking at, well, how many repetitions there are, the number of ways that we can arrange what we've chosen. So we've chosen 4 things. There are X factorial ways to arrange those 4 things, or 4 factorial ways to arrange those 4 things. Okay. And then if we break this down even further, we know that NPX is N factorial over N minus X factorial. And then this is just times X factorial. So I'm not going to get into the algebra of this, but this X factorial can go in the same denominator as the N minus X factorial. This is the same thing as doing NPX times 1 over X factorial. So the NPX is N factorial over N minus X factorial. This is the NPX part. And then we're multiplying by 1 over X factorial. So that's why the X factorial can go in here. Dividing by X factorial is the same thing as multiplying by 1 over X factorial. It's like dividing by 2 is the same thing as multiplying by 1/2. Okay, same idea. So this is the formula for combinations. And like I said, I tend to do it where if I have 7C3, for me, I would do 7 times 6 times 5 over my 3 factorial, 3 times 2 times 1. Okay, this is the same thing as doing 7 factorial over 4 factorial. That's the 7p3, and then 3 factorial. Okay, let's take another one. 8c2. For me, I like to calculate it as just 8 times 7 over 2 times 1. But this is the same thing as 8 factorial over 6 factorial. That's the 8p6. And then I just divide by the 2 factorial. Okay, so the 8 factorial over 6 factorial is the 8p6. The 7 factorial over 4 factorial is the 7p3. And then division by 3 factorial. The 3 factorial is the number of repeats of each of those permutations. Here, 2 factorial is the number of repeats of each of those 2 permutations. Okay? Okay, so now that we know what permutations and combinations are, let's use this. Okay, so I'm going to start by just looking at different arrangements. We're going to actually use letters again. And then we're gonna do probability. Okay. So let's take a second, and the whole next part of this is in how many ways can we arrange the letters. Okay. So you're gonna see this problem multiple times. Let's say, in how many ways can we arrange the letters in the word, let's say, love? Okay, when we talk about problems like this, we're saying order matters, okay? LOVE is different from EVOL. So order matters here. Whenever you see a problem like this, order matters. So this one isn't so bad because all of the letters are different. So you have 4 possibilities for your first letter. You have 3 possibilities for your second, then 2, then 1. And since order matters, we're just talking about permutations. So this is 4 factorial. 4 factorial is 24. I know some of these off the top of my head just because I've done them so much. So this is pretty standard. If you take, in all of these, it's the same thing. In how many ways can we arrange the letters? I'm not going to constantly write that. I'm just gonna write in the word, okay? So let's take another one, but this time we're gonna say in the word, computer. So again, we're using all the letters. Order matters whenever we're asking a question like this. So how many letters are there in this word? There are 8. So we have 8 possibilities for the first, then 7, then 6, 5, 4, 3, 2, 1. This is 8 factorial. You don't have to write this out every time. You can just say 8 factorial, that's fine. And you'll see on most scientific calculators, there is a factorial. So we could just write 8, and then we press the factorial button, and you get your answer. In some scientific calculators, you might have to type in the factorial first, and then you press 8. It kind of depends on the calculator. The TI-30X, you would type in 8 and then the factorial button, okay? Otherwise, I'm not sure. So you might have to ask, or you might have to look in a manual, okay? Okay, in both of these, there's no repetition, meaning every letter is different, okay, in both of these. So let's just, I'm gonna add that here because things change. So let's take an example where that's not the case. Let's take, again, I'm just gonna write in the word. Let's say that we have in the word happy. Well, now we have 2 letters that are the same. These P's. The P's are both the same, okay? Well, there's no difference between HEPPY and HAPPY, okay? There's no difference between PAHPY and PAHPY. There's no difference between that. Those are the same, and yet when we do, there are 5 letters here. When we do this, it makes it seem like they're different, right? It's saying PHAPY is different from PHAPY. So let's take that example. Imagine that this had a 1 and this had a 2. Well, when we do the 5 factorial, it's treating these as different, it's saying, okay, well, P2 and P1 could switch places, and it's counting that as different permutations. But they're actually the same. These P's aren't different. These two are the same permutation. There really is no difference between the P's. There's no difference. Between PHAPY and PHAPY. You can see it when we write it, right? There's no difference between them. But 5 factorial treats them as if they are different. So we need to get rid of the repetitions. And we're going to do that in the same way that we got rid of the repetitions for combinations. And the way that we did that is we divided. And we divided by the number of repetitions of each permutation. So how many repetitions are there of each permutation here? There are 2. Because either we could have P1, P2, or we could have P2, P1. There are 2 repetitions for each permutation here. And it's really 2 factorial. And I'm going to put in that factorial. It doesn't matter here, right? 2 factorial is 2 times 1. But I'm putting it in because if we have a letter that repeats 3 times, then things change, okay? So what this is, our answer here, this is one case where the permutation is the same. We have permutations that are the same. It's just 5 factorial over 2 factorial. And 5 factorial is 60. So there are really only 30 permutations here. 5 factorial over 2 factorial is 30. Okay, so we only have 30 permutations because these are being counted as different, but we're going to cross out the bottom one. Okay, and we're going to say, nope, that's not different, that's the same. Let's do the same thing with a different word. Let's say in the word letter. So now we have something new because now we don't just have 2 T's. We also have 2 E's. But we can't divide by 4 factorial, right? Because we could have like T1 and T2. But then we also have E1 and E2. In other words, L, E, T, E, R, T is different from L, T, E, E, R, T, right? These are different permutations. But if we added 1s and 2s to these are the same. right? These are the same, but these are different. So let's talk about what that means. What that means is that we're looking at the number of ways that we could rearrange the e's in the same permutation, and we're looking at the number of ways that we can rearrange the t's. We're not doing, so we're dividing again, okay? In this case, we have 6 letters. But we're not going to divide by 4 factorial because we don't have 4 e's here. We have 2 e's and 2 t's. We have to treat them separately. We have to say, okay, well, how many times are the e's going to be rewritten? And then how many times could the t's be rearranged? So we could have E1 and E2 here, or E2 and E1. And we could have T1 and T2, or T2 and E1, and T1. Here, the same thing is true, right? We can switch the t's here, or we could switch the e's. So we actually have we have lots of different repetitions, okay? So how many different ways can the e's be rearranged? For each permutation, the e's could be arranged in 2 factorial ways. And the t's could be arranged in 2 factorial ways. This is the number of ways we can rearrange the 2 e's and this is the number of ways we can rearrange the 2 t's. In other words, we switched T1 and 2T here, but we didn't have to. We could have left T1 first and T2 second. That would have been fine, okay? The T's and the E's are independent of each other. So that's what we're saying here. So this is telling us we're doing 6 factorial, and we're dividing, and order matters here, okay? We have to put in parentheses because otherwise it's going to multiply first. It's going to do 6 factorial divided by 2 factorial and then multiply. So we're going to divide by 2 factorial, 2 factorial, and then we close the parentheses. Something went wrong. Let me redo that. 6 factorial. I think I didn't put in a multiplication sign, and I should have. 2 factorial times 2 factorial. Okay, 2 factorial is 2, 2 factorial is 2, so 2 times 2 is 4. So we get 180. So just as a quick note, I want to be clear. Two factorial times 2 factorial is not equal to 4 factorial, okay? The T's and the E's are not the same letter. So the reason why I have this second one written here is because if you divided by 4 factorial, it would be saying that these are the same, that we could rearrange the T's and the E's however we want, but we can't. The E comes second here. It has to come second in the next permutation if we want it to be the same permutation. Here now it comes third. So if we divide it by 4 factorial, it would be as if we treated the T's and the E's as the same, but they're not, okay? Each letter gets its own separate factorial down here. Let's take another example. Let's rearrange the letters in the word curiosity. I'm actually going to change the word. This doesn't have, it doesn't have enough variation. Let's do it in the word dependent. So in this one, you're going to pretend that there are no repetitive letters. So if there are no repetitive letters, there are 9 letters here. So it would be 9 factorial. Okay, so that came from the 9 letters. Then we have to divide by the repetitions. So we're going to look at letters that repeat. So the D does repeat. It repeats twice. So for every permutation like this one, we can either write it as D1, D2, or D2, D1. And that's the same because we're here differentiating between the Ds as a 1 and a 2, but they're really not any different. So for the Ds, there are 2 factorial repetitions. Now let's look at the E's. So there are 3 E's here, which means that we can arrange it in 3 factorial ways because we could have E1, E2, or E3 here, and it would be the same. Here we would have whatever we didn't use of those, and this would be the last one. So there would be 3 factorial for the E's. The P's, there's only 1, so we don't have to worry about that. The N, there are 2 of them. So we could arrange it as N1, N2, or N2, N1. So it would be 2 factorial. And then the T at the end, it doesn't repeat. Okay, so the 9 factorial is if there were no repetitive letters. This 2 factorial we got from the D. This 3 factorial we got from the E. And this 2 factorial we got from the N. Okay, and you can see why it's 3 factorial because there are 3 times 2 times 1 ways to arrange these E's. Let's try one more. Let's do it in the word Massachusetts. So again, we're going to count the total number of letters. So there are 3, 6, 9, 12, 13 letters. So we're going to have 13 factorial on top. That's because that's the number of letters. And then we're going to divide by the number of repeats. So we're going to look across. There's only 1 M, but there are 2 A's. So we're going to divide by 2 factorial to get rid of the way that the A's repeat. Then we go to the S's, and there are 4 of them. So there are 4 factorial ways to arrange them. The A we already took care of. There's only 1 C, so we don't have to worry about it. There's only 1 H, 1 U, 1 E, but there are 2 T's. So the 13 came from the fact that there are 13 letters. This 2 factorial is from the A's, the 4 factorial is from the S, and this 2 factorial is from the T. Okay? Okay, so this is one way to figure out the number of ways to arrange letters. So this is really looking at it from the idea of permutations. We take the total number of permutations and then we divide by the repeats. That's what we're doing here. The number of permutations of the letters and divides by the repeats. But there's another way to look at this. And the other way to look at it is treating it as if we have these empty spots that we have to fill, okay? So for each of these, there's a second method. So let's take in the word happy again. So now, let's put the letters into empty spaces instead. So what we're saying here is that we have 5 empty spaces. And we're choosing one of them for the H. And how can we do that? Well, there are 5 spaces and we're choosing one. Okay, let's suppose then that we put the H into this first space. Okay, into that space. Well, now we're going to have to put in the A. Well, there are only 4 spaces left. So if there are only 4 spaces left, we have 4 spaces, and again, we're choosing only one of them for the A. And fundamental counting principle says we multiply. For every way that we could put the H, there's 1 space that we could put the A into. So now we have 4 of these to put the A into, but if we put the H over here, we would have 4 of these to put the A into. So we have 4 spaces left. We're choosing one of them for the A. Okay, how many are left now? Let's say that we put the A in here. Let's just say the A goes here. Well, now we have 3 spaces left. And we're putting in the P's. Well, there are 2 P's. So we're choosing 2 spaces for the P's. 3 spaces left. We have to choose 2 of them. For the P's. Right? So let's put the P's here and here. The reason why it's a combination and not a permutation is because whether we put P1 here or P2 here, it doesn't matter. So the order in which we choose these spaces doesn't matter. And now what's left? Well, there's only 1 space left, and we're choosing that space for the Y. So notice when we get this number here, this is the previous minus the number that we chose, right? So this number is 3 minus 2. This number is 4 minus 1. This number is 5 minus 1. So this is for the H, and the order in which we do this doesn't matter. So in other words, if we decided to put in the A before the H, it doesn't matter. This is for the H, this is for the A, this is for the P, and this is for the Y. Okay, this is the same thing as 5C2 times 3C1 times 2C1 times 1C1. That's what I mean here. That if we put in the P first and then the H, the A, and the Y, you actually, mathematically, this is the same thing as this. There's no difference, okay? That's because in our numerator, we have 5 times 4 times 3 times 2 times 1. And in our denominator, we're gonna have a 1 here, a 1, 2 times 1, and a 1. And we still have 2 times 1, a 1, and a 1, and a 1. Okay, if you didn't understand that because I went through it quickly, it's okay. Just the idea is that I want you to get is that the order in which you put the letters into the blank spaces does not matter. Okay, you get the same answer in the end. Let's take one of the others that we did. Let's do letter, okay? So this is just a second method. You can use whatever you want. They both work. So in this one, again, we have 6 empty spaces now. So how can we do this? Well, we have 6 spaces. We're going to choose one of them for the L. So let's say that we put the L over here. Now we only have 5 spaces left. We're choosing 2 of those for the E's. So we're gonna put the E here and here. We're just choosing, it doesn't matter, okay? That 5C2 is telling us in how many ways can we do that. I'm putting it in here just to make you see how many spaces we have left. So we put in the 2 E's, we have 3 spaces left for our remaining letters. Now we're going to put in the T's, and we have to choose 2 of the spaces for the T's. And now we have 1 space left, and we're choosing that space for the R. So notice the N and the R are equal here. So the 6C1 was for the L, the 5C2 was for the E, the 3C2 was for the T, and the 1C1 was for the R. Again, another way of doing it. Let's do, in the word dependent, it gives us the same exact thing. So in this one, we have 9 empty spaces. So we're going to choose 2 of them for the D's. Again, it doesn't matter which ones. Now we have 7 spaces left. And we're going to choose 3 of them for the E's. The order in which we choose those 3 spaces doesn't matter. If we chose this space first, and then this space, and then this space, ultimately they would all still have E's. So that's why we're using the C instead of the P. Then we have the D, the E. We're choosing 1 space for the P. So there are 4 spaces left now. We're choosing 1 of them for the P. So let's say we put the P here. Now there are 3 spaces left, and we're choosing 2 of them for the N's. Well, now there's only 1 space left, and we're choosing it for the T. So again, the order doesn't matter, but what we did is we did the D first, then the E, then the P, then the N, then the T. It does not matter, okay? This will look a little bit different if you change the order. For example, if we did the P first, it would be 9C1. That's okay. Ultimately, when we multiply, it winds up the same, okay? So this is the same as 9C1 times 8C2 times 6C3 times, this is if we did the P first, there's one P. Then we did the D, there are two Ds. 3C2 and 1C1. Okay, so in this case, we did P first, then D, then E, then N, then T. These are equal, so the order in which you put in your letters does not matter, okay? Let's do the last one. Let's do Massachusetts. Hopefully I'll be able to fit it here. So in this one we have 13 blanks. So if we do the M first, there's only one M. So we have 13C1. There's only one A, so we have 12C1. I'll just put them in order here. There are 11 spaces left, and we're going to use 4 of them for the S's. Because there are 4 S's. Now there are only 7 spaces left. Sorry, there were 2 A's. So let's make the 12C1 for the C. And now we're going to do the A's. So there are 7 spaces left, and there are 2 A's. Now there are 5 spaces left, and 1 H. 4 spaces left, 1 U. 3 spaces left, 1 E, and there are 2 spaces left and 2 T's. Okay, I don't know if you'll see the letters here, but I'll try. We put in the M first, then the 12C1. I said let's switch it to the C, because there was 1 C but 2 A's. There were 4 S's, 2 A's, 1 H, 1 U, 1 E, and 2 T's. Notice our N and our X are the same here, okay? They're the same because we have 2 spaces left. The number of letters that we have left to fill should always equal the number of spaces that we have left in the very end for the last letter. Okay, so this is the second method for organizing, for finding the number of arrangements. Okay. Okay, now let's look at probabilities. So there aren't that many problems like this. We're just going to take a bunch, or a small number, not that many. Okay, so I had to pause and restart, so you're seeing a lot of stuff that just happened to appear on the page, but I'm going to go through and I'm going to explain it slowly, okay? So the next set of things I said that we're going to talk about are probabilities with these combinations and permutations, okay? So we're going to be using the fundamental counting principle a lot. We're going to go through just a few examples of these probabilities with permutations and the fundamental counting principle. So Suppose that we had a 7-digit phone number, and we're going to ask 2 questions, each one slightly different than the other. So we're going to start with, you are trying to call your sister, and it's a 7-digit number. Okay, you know the area code, so it's only the 7 digits. And now we keep all of these numbers in our cell phone. So we think that we know the number, but we're not sure. Okay, we want to know what's the probability we dial the correct number if we remember just a few things. Okay, of the 7 digits, we remember that the first digit is odd, the second digit is a 2 or 3, the fourth digit is a 6, and the 7th digit is greater than 6. We call these the restrictions, or we could also call it conditions. You'll hear it referred to as both. So that's one question. The second question that we can ask is, what's the probability that if we dial any number at random, any 7 digits, it'll satisfy these conditions? Okay, 2 separate questions. So let's answer each question. So first of all, we have total outcomes over desired outcomes. Let's start with this first question, okay? And the first question is going to go directly into the desired outcomes. This total outcomes is irrelevant to the first question. So that's why I just ignore it, okay? That's irrelevant to the first question, okay? So our desired outcomes are really the possible phone numbers that we have. So we have 7 digits. We know that the first digit is odd, so we don't have to dial all numbers. We are only dialing either a 1, 3, 5, 7, or 9, so there are only 5 possibilities. For the second digit, it's a 2 or 3, so we're only dialing 2 possible numbers, a 2 or a 3. The third digit, if you notice, we don't remember because it doesn't say anything here, so there are 10 possible digits. The fourth digit we know is a 6, so we're dialing a 6. Be careful here. A lot of people put the 6 in the wrong place. There's only 1 digit that we're dialing, not 6. 1 digit, and that digit is a 6. The fifth and the 6th digit we don't remember, so it's going to be 10 possibilities. And the last digit is greater than a 6, so it's got to be a 7, 8, or 9. So if we dial only numbers that satisfy these conditions, we're going to dial 30,000 numbers. And the probability that we're going to dial a correct number, well, there's only 1 correct number. So we're dialing 1 out of a possible 30,000. So the probability that we get a correct number, the desired number is our sister's number. So it's 1. And then the total number of numbers that we could dial is 30,000. And 1 divided by 30,000 is 0.0. Let me make sure I got that right. Yeah, it's 0.0003. Now over here, this is the one that we're talking about, okay? Like I said, I had to pause the tape, so things just appeared. This e to the -5 is not how we write it. What this tells us is that we're going to move this decimal point 5 spaces to the left. And if we move it 5 spaces to the left, that requires us to stick in 4 zeros, okay? So it's 0.00003. So this is the probability of getting a correct number. Then we have the solution to the second question. So the solution to the second question is actually here. This is the probability of dialing a number that satisfies the conditions. Asking the question in 2 different ways, and it gives us 2 different answers. So if we closed our eyes and we just dialed any number, well, there are 10 million possible numbers that we could dial, because if there are no restrictions, then there are 10 possibilities for each number. So 10 times 10 to the times 10 times 10 7 times is 10 million. So there are 10 million total outcomes. But we already discovered that there are 30,000 of them that satisfy these conditions or have these restrictions. So that's 30,000 divided by 10 million. And that probability is 0.003. So notice in one question, we're asking the probability that we satisfy the conditions. And then in the other question, we're asking for the probability of a correct number. So correct number has a 1 in the numerator. And then these desired outcomes, the ones with the restrictions, is what goes in the denominator. When we're talking about satisfying the conditions, then this desired outcomes, it goes in the numerator, and the 10 million goes in the denominator. Okay. Now we're going to do the same thing with 3 and 4. So we're going to do this one, correct one first. Okay. So let's say, for example, that you lost your car in a parking lot and you get all panicked. A police officer comes over to you and says, okay, well, what was your license plate? And these are the things that you remember. So you remember that the second character, okay, the first character, sorry, is the letter. Second character, these quotes just means it's repetitive, okay? Second character is a vowel. Third character you remember as an R or an H. Fourth is an even number. Just so that you know, 0 is even, okay? 0 divided by 2, anything divisible by 2 is even, so 0 divided by 2 is 0, it's an integer, so it's even. 2 minus 0 is, 2 minus 2 is 0, so it's even. The fifth number the fifth character you just remember as a number, and the sixth one you remember is a 4, so you have an exact number there. Okay, so let's go through and calculate these probabilities. So we're going to do the same thing because eventually we're going to ask this fourth question, what's the probability we get a license plate that satisfies the conditions? So we're going to calculate these total and desired anyway. So total outcomes is as if we closed our eyes and we just chose any license plate. So from before we saw the license plate, first 3 characters are letters, second 3 are numbers. So there are 26 letters in the alphabet, in the English alphabet. So if English isn't your first language, 26. So if we know nothing about the license plate, it's 26 times 26 times 26. We have no restrictions here. Times 10 times 10 times 10. And from earlier, we know that that's 17,576,000. Now we have desired outcomes. Okay, so we know that the first one it told us, all we know is that it's a letter. So there are 26 possible letters. Second one we know is a vowel. So the vowels in the English alphabet are A, E, I, O, and U. Y is not a vowel. The third one we knew was either an R or an H. So there were 2 possible outcomes here. The next one we knew was an even number. So it could be 0, 2, 4, 6, or 8, which means that there are 5 possibilities. The 6th character we said was just a number. We don't know what, so there were 10 possible digits. And then the last one had to be a 4, so there's only 1 possibility. And fundamental counting principle says we multiply these, so we get 13,000 possibilities. Okay, so let's answer that third question first. So the third question was, what's the probability that you guess the correct license plate? Well, there is only 1 correct license plate, so it's going to be 1 over 13,000 because there are 13,000 possible license plates that you may guess, okay? Because they satisfy these conditions, and you're not going to guess a license plate that doesn't satisfy what you remember. So it's going to be 1 over 13,000. And that we can see is we see this -5, so that means that we're going to have a decimal point, and then 4 zeros, 7, 7. Okay, that -5 says move this 5 spaces to the left. That's what the negative means, move to the left. And you need 4 zeros. So we have 0, 0, 0, 0, and 7, 7, 7.69. The 9 after the 6 says move it up to a 7. Okay, now let's ask that other question. We're going to close our eyes, guess any possible license plate, and we want to know what's the probability that it satisfies the conditions that we set forth over here, okay? Well, the number of desired outcomes, the number of license plates that satisfies those conditions is 13,000. The total number of license plates that exist in this state is 17,576,000. So it's going to be 13,000 over 17,576,000, which gives you 0.00074. Let me make sure I don't need another zero. No. Okay. So essentially we have two different questions. The first question is the probability of getting something correct. And this is going to be 1 over the number of desired outcomes, essentially. And the second one is the probability that we satisfy conditions. And this is going to be your number of desired over the number or over the total number. And the reason why this is 1 over the number of desired is that our number of desired here is the total outcomes that we would try. One example of how we would use permutations and combinations with probability. And that's mainly permutations. Okay, we would say permutations because the order of the license plate matters. A license plate that starts with GNH is different than a license plate that starts with GHN. Okay, let's take another problem. Let's say that we want to create a group, so different type of problem. So this would be probabilities with combinations. And we'll just do a few of these, and then this is it for probability. Okay. So in this one, let's just start with so if we have 8 boys and 6 girls. That should be it. We want to know what's the probability if we choose 5 people at random, we choose 3 boys and 2 girls. Okay, so in this case, we're looking for something very specific. We want 3 boys, we want 2 girls, and we know how many boys and girls there are. So again, we're going to choose total outcomes. So total outcomes would be choosing 5 people with no restrictions. And order doesn't matter. We have an indicated order. So if you're wondering, you would either be told order matters, or you would be given something that indicates order matters, like the first person is a president, the second is a vice president, the third is a secretary, or the first person is a facilitator, the second is a note taker, the third is a timekeeper. But here, we're not given any of that, and we're not told that order matters. So you can assume order doesn't matter, okay? So the total outcomes, well, we have 14 people in total, and we're choosing 5 of them. So that's the total outcomes. But now we have to figure out, okay, well, what's the desired outcomes? Sorry, this is on a separate page. Well, we want to choose 3 boys, and we have 8 boys in total. So think of it as if we put these different groups in different rooms. We put the boys in one room and we put the girls in the other room. And the 8 boys are in a room, and we're going to choose 3 of them at random. So for the desired outcomes, there are 8 C3 that we're choosing of the boys. And then we go into the room with the girls, and there are 6 of them. And we're going to choose 2. There are 6 of them, and we're going to choose 2. So for the girls, it's 6 C2. Eight boys, we're choosing 3. Six girls, we're choosing 2. So the top is the restrictions, okay, the desired outcomes over the total outcomes. So the probability of getting 3 boys and 2 girls is 8C3 times 6C2. And don't worry about plugging this into your calculator for now. Just this would be what I'm looking for here. Okay, if you give this answer, this would be a full answer. Let's take another example. Let's say, so I'm going to put a 1 over here. Put a 1 here. And now we're going to do this. So let's suppose that we have in a class, in a performing arts class, we have 10 actors, so people who only want speaking roles. We have 15 singers. We have 8 dancers. And for a performance, we need 6 actors, 4 singers, and 7 dancers. So we want the probability answers if we choose 17 people at random. This PPL is just people. Okay. So we're going to need total outcomes. So total outcomes. Well, we're choosing 17 people, but we have 10 plus 15 plus 8 people in total. So we have 33 people in the class. Okay. We're choosing 17. So the total outcomes is 33C, 17. Now we need the desired outcomes. Desired outcomes. So in the desired outcomes, we're putting the actors, the singers, and the dancers all in separate rooms. And then we're going to the actors' room and we're choosing 6 out of the 10. We're going to the singer's room, and we're choosing 4 of them. And then we go to the room with the dancers, and we're choosing, of the 8 dancers, we're choosing 7 of them. Fundamental counting principle says we multiply. So this is the number of desired outcomes. Now, if we want the probability now of getting 6 actors, four singers and 7 dancers, this is going to be 10C6. Sorry about that. 10C6 times 15C4 times 8C7 over just putting all 33 people in the room and choosing 17 of them. So this is our answer here. So the 10C6 is the actors. The 15C4 is choosing the singers. And the 8C7 is choosing the dancers. Let's take one more example. Let's go back to the deck of cards that we like so much. Let's say that we want to know what's the probability of choosing 2 aces and 3 hearts. Let's change this to 2 spades. Or we'll write clubs. Clubs is nice. 2 clubs and 3 hearts from a deck of cards. Okay. Well, our total outcomes have 52 cards, and we're choosing 5. Our desired outcomes Well, we have 13 clubs, and we're choosing 2 of them. And then we have 13 hearts, and we're choosing 3 of them. So we want to know, what is the probability of choosing 2 clubs and 3 hearts? Again, there's nothing to indicate that order matters, which is why we're using combinations. This is over 52. C5. So this is our probability. Okay, so it's as if you're putting each different type of things in a different room. So we put the clubs in like a different spot, then we put the hearts, and if we did 2 clubs out of 13 in total and 3 hearts out of 13 in total, and we multiply because of the fundamental counting principle. So I'll put that up here too. So we're always multiplying. Because of the fundamental counting principle. This is it. This is all of the basics of probability. We're still going to be doing a little bit, we're still going to be doing probability, but it's going to be really different. It's going to take all of these things and put it together. But this is the basics of probability, and this lecture, along with I think it's 3 lectures that came before this, are what's going to be on your next quiz. And then what we do in the following lectures have to do with something called the distributions, and that's not going to be on this next quiz.